Excellent. Thank you very much. So, in the program, there's also a subtitle talking about getting the best out of the beast. So, who or what is the beast? Well, I'm sorry to say, in this case, it's AutoSAR. And I'm going to back up this view a little bit with a recap, which is also something we need for understanding the templates. So let's look back um, a few years, exactly 2 years, when we gave a talk um, at the AutoSAR Open Conference in Tokyo. So we're going to have a quick recap of that presentation. And the question we want to tackle at this point here is, well, efficiency. Does it really matter that much? Yeah. Talking today about the AutoSAR efficiency templates. So efficiency in automotive projects, does it really matter that much? So, and let's have a look, okay? You see, I'm picking out a few slides from 2 years ago now, and the first one here is from a platform. So it's a real customer project, not just a project, it was a platform. So there were actually 19 vehicle models affected. And I mean, this is a CPU load view now of their software. Look at how big the piece of the cake is that goes to the RTE, yeah, which enables the consistent data communication. But actually, this is not what you have in mind when you write automotive software, right? That so much time is spent in the RTE. There must be a better way. So 30% of CPU load only for the RTE. Second example I gave was, again, a platform. It's always platforms, yeah? So the impact on the project is really very big. So here we see, again, roughly 30% on each core that is used just by interrupt suspension, right? So not even copying the data yet or anything. It's just interrupt suspension that eats up 30% of the CPU load. And here you see some other figures. So this on this Infineon RX, the interrupts get suspended on core 1 over 343,000 times every second. Of course, there's not much time to do anything else in the end, right? So, and finally here, this example where the processor was overloaded and the customer, again, a platform, of course, the customer evaluated the costs of using a more powerful device and having to spend more money on that, of course, and to all give a lot of money to the suppliers who would all need to change their software and so forth. They evaluated the cost to be 160 million euros. So that is really draining a lot of money. Thank goodness all of these 3 projects could be optimized. They're in production in the meantime, and everything's fine. So no more problem here. So obviously, I think this is a figure that shows that efficiency really does matter. There are also not just efficiency problems, but also safety problems, reliability problems, like you can see here. With this was related to ECC tasks and the pitfalls which are related to that. You see like a lot of failed task activations here. And yeah, customer wasn't even aware that this is going on in the software. Sporadic overload, task force, SOP in danger. So that was the background of this. Okay, that was about the recap. Now let's take a quick look about open source versus how things are tackled in automotive very often. Okay, so because this conference here, this year, the 17th AutoSAR Open Conference, is also about open source. And well, examples and demos outside AutoSAR. Open source projects typically come with easy entry, okay? So people search for something on the internet, they search for something on GitHub, they have the readme.md, and that is their starting point. Yeah, this is what people expect, and an easy start, easy to use, Okay, this is comes also with intuitive examples and demos, right? And well, not always, but very often with extremely good documentation. YouTube tutorials, yeah, a lot of that. And because they use that in their private projects, maybe also in their previous companies or whatever, there is a certain expectation to find something also when you use AutoSAR. At least that's my assumption. So let's take a look at real projects again, okay? And this is, by the way, this is an ASIL D. This is a safety relevant project, okay? And they ran into problems, and I did some coaching there, and then I bumped into this source code comment here. Yeah, this. Okay, no, it was not ETAS, ETAS stack. So this file contains a stripped down CPU description for a tasking linker. It's also not a tasking problem, right? Definitely not. It was created using a trial and error method, starting with an empty file and adding only the portions that the linker complained about. So they took some demo application and then a big hammer, and then they smashed it, yeah, on that application until it kind of did what they thought it should be doing, and then called it, okay, this is the basis now for our ASIL D application. Come on, this is pretty much insane, right? So they take whatever is available. I mean, the alternative is not having anything or starting completely from scratch. So many projects are really quite desperate. Yeah. Okay. And then once it's working, it's not touch and reconsidered question. Well, until then, very often towards the end of the project, you run into real problems, and then you need to get it right. So this is how safety relevant projects, not always, of course, but sometimes are developed, and there must be a better way. And that brings us now to the AutoSAR efficiency templates. So 2 years ago, I was talking about problems. So I'm the problem guy, and now comes the solution guy. I hand over to you.
Thanks, Peter. I probably need the clicker as well. Right, so, and actually, if you look at the example that Peter's just shown with, okay, we start with an example and we just try and randomly add things until it works, we've got AI to do that now, so it's much better. Okay, so we started looking at this in terms of trying to, instead of finding problems at the end of projects where things are on fire, how can we try and start encouraging people to do good design and use best practice up front? So if you look at the AutoSAR standard, there's lots of stuff in it, absolutely huge amounts of stuff in it. But we don't really give a lot of good guidance about how and when to use those features. It's like, here's a massive list of features, knock yourselves out and come up with useful applications for them. But actually, the vast majority of projects need a little bit more direction. So in terms of success through AutoSAR projects, we've identified 3 things that are kind of important here. So the first thing is an efficient stack implementation. Your underlying stack has to be reasonably efficient, and then you can try and leverage the best out of it. And we can do that kind of thing at ETAS. The second thing you need, which is more subtle, is efficient configuration of the stack. So AutoSAR is like, if you think about it like a programming language, you can write rubbish in any language. You can write rubbish in AutoSAR, but you can also write good stuff in AutoSAR as well. So what we're trying to do is to encourage people to head towards the good stuff. And this is why we're doing the efficiency templates. And this is free. This is on the GitHub page that Peter's just showed. And then when we apply these templates, we need to start looking at, okay, what is the impact on my project? Does that make things better? Does that make things worse? Because some of these templates are going to involve classic engineering space-time trade-offs. And then being able to use Gliwa's T1 tool to be able to measure the impact of that, both in terms of the timing performance and the stack performance, really useful. So it gives you a nice way of closing that engineering loop. Let's make a change. Let's go from design best practice. Let's see what the impact of that is. So this is where we're hosting them at the moment. So there's a GitHub webpage for the efficiency templates. You can just download these. There's some examples about what they are, descriptions about what the before part was and what the after part was. Okay, the other thing we need is a couple of things from an efficient AutoSAR implementation. So if you look at AutoSAR, thousands of options. I think at the moment there are over 80,000 configuration parameters for AutoSAR. the vast majority of projects never need them. There's huge amounts of stuff in AutoSAR that is for important but really esoteric use cases. And just because something's in the box, you don't need to take it out of the box. So most projects don't need most features, and you don't need to pay to run them at runtime either. And the second thing is that actually what you can start doing by looking at the configuration and the stack together is you can start trying to use, we do a lot of code generation in RTACAS, so anybody that's using our AutoSAR solution, you'll see this all the time. But you can start using your intelligence about, okay, what is the configuration and how do we leverage that in things we may or may not need to generate in the stack? We can actually come up with really efficient implementations. And essentially, as an AutoSAR vendor, our job is to try and get you the smallest amount of code and data as possible into your ECU. That's what we're trying to do. We're actually trying to save you BOM manufacturing costs for hardware by giving you less software. You need to do exactly what's required, but nothing more and nothing less. Okay, so if we have a look in the OS, for example, there's a whole bunch of stuff in the OS to do with queuing. So yeah, if you build a queue, you can queue tasks and can queue task activations. But you know what? If you want to build a really small queue, just make sure it's a unique priority and it's a counter. And then you can turn that queue and all the logic to maintain that queue in RAM and to manipulate that queue with code. You can just turn that into a simple byte and increment it and decrement it as it's queued. So these smart implementation decisions you can make when you build things. So this is a really good example. You look at that in the slides later. But now you can make really small and efficient implementations of things. So what do those kind of efficient design choices allow us to unlock? This is a slide we've used quite a lot. This is our entire operating system for a production ECU powertrain controller. That's the OS. It's about 1.5K and it's tri-core instructors if you want to disassemble it. That's it. And we get that by essentially applying a huge amount of optimizations, but being derived from by a really efficient configuration as well. So it's so small, it fits here. So that takes us on to the templates then, right? So we're going to look at a few templates. There's 4 cases here. Some of them share some similarities that you will see as we go forwards. But just to give you an idea of by how you can drive optimizations through your system by choosing sensible configurations. They don't purely apply to our implementation of AutoSAR. So anybody else's implementation of AutoSAR, you should be able to leverage these as good design practice within your systems. We might be able to do slightly more optimization in some cases, but nevertheless, these are sort of generally useful optimizations. So the first thing is RT implicit communication. So using implicit read and write access to exchange data. Well, why do we want to do that? Isn't all that copy semantics expensive? And the answer is yes, if you always have to copy, but in most cases, you don't have to copy. So if you look idiomatically at how things exchange data, you don't need to copy data all the time. So as soon as you have a set of readers and writers that share the same preemption level, what that means is you don't need to get a copy. You can just read and write global variables. And there's a whole set of algorithms inside that essentially get reflected in the implicit communication semantics of the RTE called state-based message semantics. This really allows you to get efficient communication using the minimum amount of data copies and without using an official communication mechanism. And the way this helps is if you use this model in the RTE, you can save significant amounts of global data RAM and significant amounts of code, right? How big is this, right? So let's just take an example. Okay, so here we've got 2 things. So we've got the copies on the left hand side. As soon as we move these from explicit reads to implicit reads, all of the data's disappeared. This is all stuff that we're just caching in RAM, and it's just disappeared. We don't need it anymore because it's not required, because we can still guarantee the integrity of that data without creating those copies. And then you look at the code to manipulate it. So here's a load of RAM being wasted. Here's a load of flash being wasted. Saved. Magically disappeared. No change in the semantics of the model. No change in the behavior. All your data is still consistent. It's all working. And now it's taking a lot less space and time.
Just one comment at this point. It's not just you're saving flash. Of course, the code also needs to be executed. So it's also saving runtime. Okay, so this is exactly
It's,
the
it's
first.
a triple whammy. Yeah.
Yeah, yeah. You win with respect to RAM, flash, and runtime. So this is exactly the example with a 30% RTE, which then boiled down to something you could hardly see on that figure anymore. So yeah, this really, really makes a big difference. And I just want to underline one aspect. This comes with 0 changes on the functional level. You don't have to touch your functional code. Yeah, don't. I just want to make that sure. It's just about how you configure the operating system.
And we've got a simple example here. There's 3 interface elements and 10 ports. 21K less data. 21K less RAM in the system for this. That's actually, on a small device, that's a huge amount of space saving. And as Pete says, there's a huge amount of time saving as well. So in the top, the task doesn't have to do any data copying, so a lot less time-consuming jobs eliminated. And if you look at that, we've got an almost 5% reduction in execution time here. So at the top, we've got 5%, 4 and a bit percent CPU load for the 10 millisecond task, and 1 and a bit percent for the 100 millisecond task. Turning all this into implicit communication, we've now got it at 0.75% CPU load for the 1 millisecond task and 0.024 for the 100 millisecond task. So that's basically 5% of the CPU loads just been saved. Thinking about buying a more expensive processor, don't need to do that anymore because you've just saved 5%. There's lots of stuff like this in AutoSAR that you can do with really efficient configuration. So we've gone from, you can see that here, you've gone from 405 microseconds in the top to 75 in the bottom and 166 in the 100 millisecond task down to 2 in the bottom. And we're just saving it. So it's a massive drop in CPU loading here. Right, next. Reduce unrunnable frequency. So this is something that is not necessarily an AutoSAR aspect, but it's something that's really valuable to think about in terms of how you're engineering the system. And the what is, do not oversample unnecessarily in your software. So here's an example for polling for Ethernet transceiver state changes. So if you've got an Ethernet transceiver, you need to basically work out when it's changing state and going to bus off and this kind of thing. So you've basically got to pull the Ethernet transceivers as the normal way of interacting with the hardware. But the time to do that state change in the transceiver, it's controlled by the transceiver hardware. And typically that's a couple of 100 milliseconds, okay? So you kind of know that independently of your CPU clock frequency, you know there's a finite amount of time on the device you're talking to that you need to wait for an interaction and a state change to help. So we can kind of start doing this. So when you start looking at where we're calling the Ethernet main function from, when it's in a millisecond task or up to a 10 millisecond task, it can have a significant difference on CPU load. So let's say you're doing it. Let's say you're doing it every millisecond and you're polling it 10 times. Actually, that's 25% CPU load in the 1 millisecond task, for example. It's really, really inefficient here. So actually, what we can then do is by changing that, so we're sampling it in a shorter amount of time. So these are the times on the bottom. We're going from running it in a millisecond task to running it in a 10 millisecond task for something that's actually probably changing every 100 milliseconds. We're now saving huge amounts of time. And so in the example that we put in the templates, there were 6 transactions checking that state receiver, and we've moved it from the 1 millisecond task to the 100 millisecond task. It's still actually detecting things in terms of the hysteresis of the device we're controlling. And now we've gone from 17% CPU load to 0.17% CPU load, obviously. You see this really frequently in systems.
Yeah, and the underlying idea here is not just related to Ethernet communication. You can apply that actually to all the code, yeah, all runnables. So I remember we've been doing some timing requirements reviews with projects. So, and as part of that, we ran through all the runnables, and for the cyclic runnables, we asked like, okay, why is this runnable executed in the 1 millisecond task, for example? And you wouldn't believe the answers we got sometimes. Very often we
don't know.
Yeah, that was one possibility. We don't know. Second option was it's always been there. And and sometimes then you can actually move stuff, as we've done here, from frequent cycles to less frequent cycles. And if you do that, if you move something from the 1 millisecond to the 10 millisecond, well, you just optimize 90% of the runtime away for this piece of code. Yeah, it's so simple and so cheap. Yeah, and sometimes surprisingly well working in real projects.
I mean, there are friends of this as well. So if you're doing anything that's mechanical and you've got some kind of rotation, so you're counting things like ABS pulses, or you're counting angular rotation in an internal combustion engine, a lot of things where people basically map those events into time instead of just using those events directly to drive the scheduling, that also has a significant impact in the amounts of execution time. So again, significant drop in CPU load. So template 3, stack optimization. This is a friend of template 1, actually, but we'll go into this in a bit more detail. It's minimizing the number of preemption levels in your configuration. Okay. So how does this help? Again, significant RAM savings here, particularly for AutoSAR-OS implementations that support some kind of stack sharing or use a single stack. So there are basically 3 ways of building the AutoSAR stack management. You either have a stack per task, and then you need to allocate space for each of those stacks, or you might be able to have things where tasks share priorities or share an internal resource, basically put those on the same stack, and then it's the maximum of that. Or you can apply that design model across the entire OS as well and just have a single stack for the entire operating system. That if you want to do that, you need to come and license the patent for that from us, because we've got some patented stuff that makes extended tasks work with them. But if you save a significant amount of stack space. If you run a single stack and you've got a chip where you might have a lot of cache in there, you might find that this also unlocks a huge amount of hardware performance in your device as well. And this one has some trade-offs. So the trade-offs are to do with it's essentially a class. So who's a computer science software person by trade here? Yeah, okay. So when we talk about space-time trade-offs, here's one. It's a classic space-time trade-off that I can basically trade off a little bit longer execution time and a little bit longer response time due to increased blocking, and I can trade that off for RAM. Why do I want to do that? Well, what are the most limited resources you've got in your system are RAM, flash, and time. Those are the only 3 variables you've got to play with, and they're all bounded in your ECU. Typically, RAM is the most precious one, followed by time, followed by flash. But obviously, for a particular project, the most precious thing is whatever you've just run out of. But it allows you to start playing around with, okay, where am I going to move some of that load to? Am I going to move it from the space domain into the time domain or vice versa? And you can have huge amounts of stack saving here. So let's have a look at this. If we do this with RTA, with a single stack model, a task dispatch it's a C function call. It doesn't get any cheaper than that. So if you've got a stack where you've got a system where you've got nine tasks like this, and you move that from a single, so the first thing you would typically do with this is, okay, on each of those stacks, I need to add a little chunk of buffer, a little chunk of overhead in case my stack measurement figures are wrong. You know, I might have not measured it properly. My compiler might not be completely accurate in its analysis of the call tree. So I add a little bit of space everywhere. If you actually put this onto a single stack, you'll find that not only have a single stack, but you can essentially aggregate all this overflow space. And you can even potentially make a slightly bigger buffer at the top. And this makes it really efficient. The second thing you can do is, let's assume that these tasks can actually run non-preemptively with respect to each other. So this is where the space-time trade-off comes. So as soon as they're running non-preemptively with respect to each other, let's say we create 3 task groups like this, then actually what happens is this, that instead of the worst case stack usage being the worst case stack of each of the tasks, the worst case stack usage is the maximum worst case in each of these 3 blocks. So this is when B gets preempted by F, gets preempted by G. And you can see here in this fictitious example, I have saved half the RAM for the stack. And this is not operating system RAM, this is the entire RAM for the entire system here. So if we look at a real example here, this is 9 tasks. This is the one that's in the templates. There's some init tasks, there's some cyclic tasks, there's some event-triggered stuff. And then we've basically grouped the init, cyclic, and event-triggered tasks together with using internal resources. Okay, we've created an internal resource. Surely that's consuming something. Shouldn't be. If you've implemented your OS properly, internal resource is free. It's basically should be in the task control block. No RAM. You can create as many of those as you like with no overhead. Absolutely perfect kind of optimization and enablement there. So here we've got basically 50% saving in the RAM. And all we've done is played around with the configuration a little bit. Yeah.
Yeah. So again, that's true for all the examples we've been given. No change to the functional software, really just configuration changes. And I just want to give another example with a real customer project. That was, I can actually state this, was HMC, Hyundai Motor Company, where we, in the first step, eliminated all the extended tasks, so all the ECC tasks were turned into BCC. Then we shared the stack, and that reduced the stack size from 100% to 20%. That's, I mean, dramatic savings in RAM. Then we applied cooperative multitasking, which is really a very, very nice approach that allows you to have task switches, yeah, but not at any point in time, but really in between runnables. So you're getting closer to the preemptive setup without really, with eliminating some of the big disadvantages there. That reduced the RAM reduction again, and so we ended up with 5% of the initial stack consumption for RAM. So from 100% to 5% RAM. The stack now was so small that it actually kind of locked itself into cache, which then made the whole thing run dramatically faster. So here was not a trade-off. It was like you save 95% of the stack RAM, and also the whole thing runs much faster. So we didn't have the time to really elaborate a lot on cooperative multitasking, but I just want to quickly point to the book where this is described, Embedded Software Timing. You can have a look at the booth, take a look there. Chinese, English versions available. There are also a lot of other timing optimization techniques in there. There's a whole chapter actually about timing optimization.
And one of the nice things about all of this is actually using technology that's standardized in AutoSAR. We're not doing anything magic here. We're just leveraging the best things that the great and the good over the last 25 years have actually added into the AutoSAR standard. There's a huge amount of essential hidden experience from literally thousands of years of embedded experience embodied in the standard. You just need to know where it is and how to use it. And this is exactly a case of that here. And last but not least, calling client-server operations. We'll do this quickly, and then we've got some time for questions. Trying to make server renewals re-entrant where possible. So this is one of these things where there's stuff in AutoSAR and you're thinking, I see the nice orthogonality there, but really did we need that? So doing client-server. So client-server, we can do it across between tasks. We can do it between CPU cores. We can do it between threads. And we can do it across ECUs and across the system. Across the system, that's remote procedure call. That's never efficient anywhere on any system, and definitely not in an embedded system in a car. But we can start doing interesting things here. So if you've got a server runnable, there's a tag that you can tell the RTE called can be invoked concurrently. Setting that value to true basically tells the RTE, hang on a minute, here's a piece of code I can just call. I don't need to create a whole amount of elaborate client-server handling mechanism for that. I can simply call that function. And if you're doing some really good software practice and you're making a set of functions, pure functions in the computer science theoretical way of doing that, also becomes really easy. If your functions are purely stateless, this is a really fast optimization. And it also, it also involves cross-core CIs calls for things that can't be synchronous. And again, the reason for doing this is there's a lot of things in AutoSAR that are what are called zero-cost abstractions, things that you can have a nice, clean design model at the application code level, and we can make it possible with next to zero flash and execution time. But there are other abstractions in AutoSAR that, even if you implement them as sufficiently as possible, they can never be cheap. So into CPU core client server can never be cheap. It's about 200 to 300 times more expensive than just calling a function call. Got some data from a very early AOC conference about that. Because you've got to set up the stack, you've got to queue messages, you've got to buffer things, and that's okay. So in practice, you might accidentally stumble over this. If you're not careful about how you do your configuration, you might find that the RTE is doing a huge amount more code and data management work because you've not quite told it enough information on which it could actually make a much more optimal implementation of that. So here are some things. Here's some data. This is a synchronous call. This is exactly the same function in 4 different models here. Synchronous call, yeah, 180, 84 nanoseconds there, pretty tiny. But as soon as we start going for, okay, and if it's a non-reentrant server on a synchronous call or it's an asynchronous call, we're talking about nearly 100 microseconds in those 2 cases to call exactly the same function, or calling it a different call synchronicity. That makes it slightly better, but it's still slow. And in comparison to this is 100 times slower than that. So telling us that you've got synchronous server calls makes a really significant difference here. Good, so these are 4 things. As we go ahead, we'll add more. There's a lot of these have been RTE specific things. There's lots of other things in the rest of Autos that also auto-optimize things. So to the summary then.
Yeah, let's have a very quick summary. AutoSAR equals inefficient. That is what I hear again and again and again from customers. Actually, not necessarily.
It's nonsense. It's basically nonsense.
It depends. It depends.
The next thing is if you take an AutoSAR stack and you take an intelligent implementation of that and with good configuration, you can get really efficient embedded software. You can really leverage this zero-cost abstraction concept I was talking about by taking that combination of good configuration and a stack that can leverage that.
Yeah, if you struggle with the optimal configuration, yeah, certainly take a look at the templates, but then just get in touch, yeah? Either with ETAS, with Gliwa, we're really happy to help.
Yeah, we've been doing this for 25 years now, so, yeah. So we've seen a lot of things and can help you know what to avoid.
And finally, of course, you need to know where you are and check how big the configuration is. Yeah, use proper kind of timing analysis. Okay, this is kind of my marketing message here at the end. And with that, we'd like to say thank you very much for your interest, and we're open for questions. Thank you.
Are there any questions? Due to time constraints, only 2. Is there any questions? Yeah?
Yes, is the question that you guys have just been talking about timing and you've just missed a deadline?
Just if there is any OEM here. The question that we keep getting from OEMs is now what to do with memory, because of course the shortage, the prices are just going up and up. I'm just wondering, are you just presenting a way of actually dealing with it and optimizing the use of memory and perhaps reducing bill of materials?
It kind of depends, does that? Because a lot of the increasing cost in memory is in DRAM pricing, but you tend to find that DRAM pricing predominantly affects the sort of interaction of things with system on a chip where you've got external RAM. The vast majority of cases on the sort of AutoSAR classic side where it's going to be on an embedded microcontroller, it's probably got internal RAM. That will have some impact, but it's not as big as it has on the adaptive platform. This does have an impact on things like when you're going to more flashless devices on the ROM side, being able to sort of squeeze into a potentially smaller flash part. But that's probably not your dominant BOM cost in the ECU as a whole. Yeah.
So generally, when OEMs come to the tier 1 supplier, so I'm from Renesas, so when they come to us, they probably ask, okay, we need a device with this much memory or this much memory. So now, when we look into something like this, can we create some type of benchmark numbers which then can be estimated during the phase when you are defining the requirements and the size of your software, which then can be used to define which hardware should be now bought by the OEM for the project?
It's a bit. I'll start by saying it's a bit difficult, and then be giving you a more helpful answer. So it's a bit difficult because that's the how long is a piece of string question, and it kind of depends on exactly what the application is doing and exactly what it needs to talk about on the network and what crypto primitives are being used and a whole bunch of other stuff. In terms of actual practice, one of the things we've started doing is to actually try and benchmark and profile this. So if you're building a Lin node, for example, you're probably talking about 100K of flash for that. If you're building a CAN node, 300 to 400K of flash. And if you build the approximate rule of thumb, if you want to guide this, is if you're putting Ethernet into an embedded device, it's going to double the flash footprint and probably double or triple the RAM requirements. So you've got to sort of, you can sort of calibrate off that. If you need more than a meg for an AutoSAR system, you're doing something horribly wrong in the configuration there. That's just really too big. Yeah.
Maybe just to add to that question. So I assume that your customers then they have kind of some database or data collection where they say like, okay, for this software component, I need so much flash and RAM and runtime. And they, after applying these techniques here, after optimizing that, they should have new data in the table. And they should be able to select a smaller device then, which might not be what you want, but the customer will be happy at least.
Yes. So do you plan to perform this type of template? So you provided us 4 or 5 different templates of how much optimization you can do. So would you plan to take like a complete full project and run this optimization for the complete stack for the application to the basic software and MCAL and see how you optimize everything when everything is compiled together?
That's what we are doing all the time as a service. So we are kind of the timing firefighters or the embedded software resource firefighters, where we go to projects and save them, right, all the time. And what we're doing here is we take the lessons learned, put that into a template, and share the knowledge. This is what the templates and also what the book is about. Yeah.
Share more.